Hello and welcome back to my show. I'm edA-qa mort-ora-y and I'm one of the programmers at Fuse, and we're making a lot of cross-platform tools for rapid prototyping and design. And one of the areas I do a lot of the work in is animation and layout, and part of that involves some graphics. Today we're going to be looking at some Bezier curves. And not really a Bezier's, is that we're actually in the middle of sort of a hackathon at the office right now, and the project I was working on has to do with Bezier curves. But I'm going to go a little bit about the background and a little tiny bit about the math. Okay, probably a bit more than a tiny bit about the math. And we're going to be going over something called the Casteljau's algorithm, and this is what you use to split Bezier curves. Actually, it was originally used to draw them. We have other ways to draw them, but this is one of the ways that you can do it, and it really helps visualize Bezier curves. And before we get too much more into that, let me show you a little bit visually what I mean, and then we can go on from there. So this is a typical Bezier curve. It's got a line, it's got an end, and there's some control points on the top. You can't see them right now, but I can move the slider and I can move the point. So this point is somewhere along the line. And this is for a variable called t. We usually call it t, right? And let me try out my new line drawing things. We have a variable called t, and that's for this down here. This is controlling t. And so as we move this around, t goes up and down, and t at 0 is the start of the line, that's the first one, and t at 1 is the end of the line. So let's just clear that. Now, the way a Bezier is defined is there's control points to it. And let me show you the reduction first. We'll ignore some of it, but you can see more of it. These outside lines, these this point here, 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 and here, these are the control points. I actually have these defined in JavaScript, and we can look at the code quickly to see what those actually are. I'll move this over so we can see. Whoops, gotta get out of there. Okay, so those are the points right here. We have 4 points. You can see how they line up. So this is the 0, 0.8. These are in origin points. So this is 0x, and 1.0 is at the bottom. So 0.8 is about here, 0.2, 0.3 is here, 0.9x, 0 is here, and 1.1 is over here. Those are the Bezier points that we have, and they define this curve through it. And if I remove the reduction, you can remember those are the points there. And I'll get to talking about what those other lines are in a second, but that's how the Bezier is defined. Now, in Fuse, in Fuse I could take these points, I put them in an observable, and I use this replace all just so I can convert an array. It's actually a little bit quicker. And so this is it's exported as points 4 because there's 4 points. And I'll get to why I'm calling it 4 points in a little bit later. Where I do this in the curve is, where's my points 4? I have it down at the very bottom here somewhere. Okay. I'll get to the rest of the UX. This bit here, we have, this is the stroke, it's a dark color, it's 5, it's using the 4 points. And you can see how it uses the 4 points. It's using the curve, this is a Fuse contract to create a curve, and it creates not just one Bezier circle, but it's segmented. I only have 2 points here. I have the first point, the second point. And the first point is at the 0, and the first control point, the control output is 1, and the next point is at the end. It's point 3 because we're defining the end, and the control point is 2. And this draws the Bezier curve. Fuse obviously does this for you. I mean, you wouldn't want to be drawing Beziers on your own, so it splits it, it defines it right there. But we want to get a little more, and today about the Casteljau's algorithm. Let's look quickly at the Wikipedia page. If you've looked at this before and you've ever wondered how do I split a Bezier in 2, well, this is the algorithm that most people point to. And it's not the only algorithm, but it's actually a really simple one. And let me just zoom this in here a bit so you get the full value of these algorithms. And when you look at it here, it does look confusing. I mean, it took me a while. I didn't understand this algorithm until I actually implemented it. So after I had it implemented and working, then I was capable of going back and understanding this algorithm. And so let's go look at what we're doing with it first. The goal is we want to split it. So this point here is I want to find this point, but we know we can do this very easily in a parametric form. And if you've done Beziers before, it's very easy to find the point on a Bezier curve. You just simply have a simple formula. It's a cubic formula because these are cubic Beziers. And you plot your t. This value t, you stick in the formula, and you get that point out. But now what if I actually want to split it? So I'm going to click the split. Now I have two sides to this Bezier. I have the green side and the red side, so the left and the right side. A second. I've got a bit of cold, so my throat's going to go out a bit of me today. Just excuse me for a bit. Now it's one thing to find this point, but how do I actually create the curve on both sides? And if we look back at my source code, we'll see that this isn't some trickery of Fuse. I've actually in the JS code actually created the two sides to it. And so when I have the split on, this is the while true, so when I'm splitting, while I have this top split on, I do two strokes. And these points are coming from the JavaScript. And I'll get to why they are, is that the JavaScript code has actually done the splitting into two for me, and then we've used Fuse to draw both points. But you notice it's the exact same full curve, just in two different colors. And this isn't just painting differently, this is actually two curves. And if I turn it on and off, you can clearly see it's the same curve. There's no variation. Doesn't matter where I split it. There's no like break. There's no weird movement or anything. This is actually the perfect perfect split that we have. And this is done in the JavaScript. And what we have in the JavaScript here is I have four sets of points. I start with points 4, and then I go 3, 2, 1. Now these names are relevant, and I'll say why in a second they're relevant. If we look at recalc. Recalc is what's actually calculating all the points for the display. And what I do is I calculate the Casteljau points t, so I reduce from the 4 points, which is actually points 4 here, and I go down from 3 to 2 and 2 to 1, and then I just replace all the exports, and this is to update the display. Now, what exactly does this mean? And, well, let's look back at that again. I have 3 series of points, and let's look at the reduction here. Each of these points is being plotted. These outside points, this line here, go back in here and I should be able to highlight this here, highlighter. So these points here, oh, I'm drawing so well. I just wanted to play this new tool. I'll get used to it more. These are the primary control points. These are the ones that we actually typed into the file. And I gotta get rid of that. These are the points here. Now, well, what about points 3? These are the purple ones here. I'm going to highlight them green. These are points 3 here. These are going to be the points 3, where they come from over here. And then we have the final ones. If I change the color of that and I say, well, let's make these blue, I'm changing the color on the screen. So these are blue, and these are points 2. And that leaves point 1. And point 1 is that one. So right here. What this does is, each time I run it, and if we look at the recalc over here, oops, escape. If we look at the recalc operation, I call the Casteljau once, twice, and 3 times. The first time it takes these 4 input points and produces 3 points. And then it produces 2 points, and then it produces 1 point. And this is the essence of what the algorithm is doing. It's reducing the number of points in the polynomial curve to 1 degree. And every time it reduces it, it actually defines the same point at time t. So we say at time t, and it reduces all of that. Let's clear all this out. And this is what the algorithm is. If you start understanding this, is what it really means is that for a given Bezier curve, you actually have the sum of a bunch of polynomials. And when you get down to this part of the equation down here, sorry, Press the wrong button, always on the wrong keyboard. So this part right here is once you understand that it's reducing each time, you can start understanding in the algorithm itself what this is actually doing. This 0 here is saying in this series, so in our case this is when we had all 4 points, and this is 0 to n. In our case we have 4, well actually 3, because it's 0, 1, 2, 3. It's a cubic polynomial, and that's what defines our Bezier. It's a cubic Bezier curve. It's degree n basically, and it's 0. And for each of these values, bi in the 0th iteration is simply the value we typed actually in here. So this is it here. This is the bi0. This is the b0, 0, and b0, 1. Okay, those are the 4 points. The notation is a bit confusing when you have series of series, and you don't have to understand that way too much. I just want to show you how it's split down here. And then you see this other weird part. It's saying, well, what's the second set of points? And let's clear the screen off. So when you saw that there, we saw in my code, the second set of points, P3, right here, we used the Casteljau to reduce it down from 4 to 3. And that's exactly what the, I don't know why tab never works correctly on Mac. Okay. This is what it's reducing. Now this algorithm is really, this is what it's saying it's reducing here. It's saying the second one, so we started at 4 points in series 0, and series 1 is going to have one last point, and you can see that over here in the n minus j. So it's series 1 is going to have one last point. So if we had 4, it's going to have 3. And this calculation here, this looks really complicated, but it's really not. This is simply saying the previous points and translate it. And if you've done a lot of graphics, you'll recognize this calculation. And if we look at the JavaScript code, actually let's look at the visuals first. So when we have these lines out here, and we have point t, so let's go to 0.75 about, it chooses this point between these two, and this point between these two, and this point between these two to get second points. If you know graphics or you've done it a lot, this is simply the lerp operation. I mean, this is all we're doing here. We're taking the lerp of these 2 points at time t. So this is what this is actually doing here, is just taking the lerp. And I can put the text tool here, and let's just say this is actually, this is more like lerp up 2 points, 0.1 t. Oh, it didn't work very well. Whatever, let's ignore that. So that is the lerp operation, and if we look at the JavaScript code, we can actually see that this is lerp, because that's how we implemented it, because it helps me understand. Escape, get out of here. So into Casteljau, what we do is for each of the points given in, with the t, the output points are simply the lerp between the 2 points at time t. And a lerp operation is, as very common, you take the one side, multiply by 1 minus t, and the other side times t. And this gives you a move in the middle. At 0.5, this is exactly the average. So when looked at this way, this code is all that de Casteljau's algorithm is. It's simply lerping between points. Now it's the implications of this that are very interesting, and what happens when you lerp through all the way down to 1 point. So visually, when you go down one step, you go from the black lines to the purple lines, you still have a kind of Bezier curve. You have a Bezier that's reduced in complexity. And now if you go down another step, you just have one line. This is the one line, and if you go down one further step, you notice this final point, this P1, that the algorithm comes out with when we have 1 point left, when all the degrees have been removed. We have a degree 0 polynomial. It's just a constant value. It says where on the original curve our time is. And this is how originally the drawing of Beziers was defined. This is how, without derivatives, without any advanced support, without any kind of derivatives, you can draw a Bezier curve very manually using this approach. If you're really ingenious, you could probably, and this would be a nice lecture, you could create a little wooden setup we have 3, 4 wooden rods, and you actually put a pencil in the middle, and you could draw it very easily from that. And that's what makes it very interesting about this algorithm, is that it's a very visual way to understand what a Bezier curve is. I mean, the name Bezier, for the guy that followed up on him on de Casteljau, seems to have taken over the name, but a lot of the work came from de Casteljau. The history I'm not so clear on, but they're very intimately related in the sense that what we call a Bezier is perfectly described by de Casteljau's algorithms of polynomials. And so this is how we can split it down. And if you had more points, in graphics we only ever care about the cubic. Some programs use quadratic. Everything supports quadratic, but you can do cubic. And quadratic is simply a curve less. So this one in the middle is a quadratic curve. It doesn't define the whole curve, but part of it. And then we can also, okay, so that defines how you draw it. Now what about splitting it? Okay, if you have any questions up to now, just let me know. I don't mind getting into math. I just wanted to show visually, and then I'll go into splitting, or just say hi if you want. Otherwise, I'll go on to the splitting, and I'll show how we get there and give a hint about what this might be useful for in my hackathon project. So now, back to this. We have this t. This is t at the bottom, and it defines where this point is. And it's based on this reduction. Now if I put split on, as we saw in the code, I'll go back there, this is actually doing 2 different points. And you notice these points, for the left side, if you remember from the JavaScript, in each step I create 4 variables, points 4, 3, 2, and 1, and each of these are the one reduction through the algorithm. And to construct my left side curve, notice I'm picking the first point in each of these arrays, points 4, 0, points 3, 0, points 2, 0, points 1, 0. This is what becomes really curious about this algorithm, is that this split here, we have 4 degrees of polynomial. We have the black point, oh, sorry. This is from P4. Alright, so this is P4. This is P3, this is P2, and this is P1. And this is how the curve is constructed. And it's the 0th one, so it's all these, it's 0, 0. It's the first item each, because each of those are a vector. And that's what made de Casteljau's algorithm so interesting, is that when I do this reduction, when I get to the final point, if I want the left half, it's curiously the first element in all of the arrays that produced during the reduction. And so it's the 0th point of P4, P3, P2, P1. And that actually produces the control points for the left side here. So if I clear this again, you can see that if you follow this line here, so we go this line, this line, this line, we have 4 points, we have a control path, and we have a Bezier curve. And this is exactly the split where we want. Exactly at time t, we have the split to the left. And the exact same thing happens with the other side. Point, 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 and point. And that gives us the rest side. We just don't use those points at the top. They're intermediate. But on the right side, rather than using the first item in each list, we go through points 4, 4, 4, and 4. It's points 1, 2, 3, 4 still. It's still points 1, 2, 3, 4. It's over here. But we use the last one in each, and it says 0, 1, 2, 3, but that's actually the last one, because points 1 only has 1 point. So points 0 is the last one. Points 2, 1 is the last one. So we take the last side of the array, and we get the points for the Casteljau. And that produces the split. And this algorithm is relatively fast. Okay, doing it this way, the generic way I've done it in JavaScript here is not particularly fast, but it explains the concept really well. You take a points 4 in, and you can reduce it 1, and each time you reduce it 1 until you get down to there being only 1 point left. And then you can construct either the final point or a curve in between. And this all has to do with splitting. And so this all comes back to why I was doing this, and part of my hackathon project for Fuse was remove the reduction. What purpose could I have for splitting? And I'm not going to show you too much more today, but in Fuse we have a lot of things that draw paths. And you can imagine if I could split the path in the middle in a reasonable fashion, I can do all sorts of wonderful things with it. And that's actually what the hackathon project will be. I'm splitting paths, and I'm using this algorithm, and I'll be optimizing it, of course, so the algorithm just hides in a sea of code. And I'm going to do the test cases first. As always, do the test cases before you do the optimization, otherwise weird things will happen. And I won't be showing what I did right now. I'm not quite done my demo, but once I'm done my demo, I'll show you guys later. But a bit of a short episode today. There's not much to the algorithm. If you want, you can go back and read once you understand the code. I'll publish the code soon, and I'll post it to Twitter then, and you can see the JavaScript code that produces this, and this runs in the current version of Fuse. I'm using the 1.5 release. It's a preview release, but it should work just fine in a previous version. There's nothing special about the Explorer. And then you can play with this code if you want to understand it a little bit better. And that's all for my show. If you enjoyed it, please subscribe. Don't forget to send me comments, ask any questions, or if I happen to forget to post the code, just give me a kick via Twitter and I'll post the code somewhere for you to look at. And once I'm done my demo of what I'm actually doing with this stuff, I'll then post a video of how I actually did it, what happens, and how I'm using this path splitting in Fuse. Okay, so thank you very much for watching again. Bit of a shorter episode, but I hope you enjoyed, and until next time.